Hello and welcome to a FlightStream tutorial. Today we will be discussing the workflow for importing a Plot3D file using component cross-section or CCS meshes. The first step is to upload our Plot3D file using the CAD Create window. And we'll load in our first component. Once we've adjusted our drawing curves, we will use the lasso to select them all, go to our Surfaces CCS mesh, and define our fuselage. FlightStream best practices state that for azimuth refinement, the key focus is to ensure capture of the shape and curvature of the cross-sections of the fuselage accurately. Similarly, for axial refinement, the key focus is to ensure that the capture of the spanwise shape of the fuselage is correct, and to add bands of refinement where fuselage-like components have junctions with wing-like components. Here we can see that we have properly refined the geometry of the nose cone for this Boeing 777ER. Now we will import our second component from our Plot3D file, which is half of the main wing. We'll select Import, then adjust the window and use the lasso tool to select the appropriate curves for our wing. Next, we will navigate to the Surfaces tab, select the CCS Wing Mesh tool, and follow FlightStream best practices for wing-like components. Set the chordwise subdivisions to 120 to properly capture the geometry of the wing-like component. Set the spanwise subdivisions to a value that will result in the stretching of the panel in the spanwise direction to be approximately 2 to 3 times the maximum chordwise edge length. Now we will import our remaining wing-like components, which consist of our vertical and horizontal stabilizer. We will adjust the spanwise subdivisions to properly reflect FlightStream best practices of the aspect ratio of the cells of approximately 2 to 3 times the maximum chordwise edge length. In order for the CCS meshing tools to work properly, the drawing curves must be ordered from root to tip. This can be accomplished by navigating to the Operations tab and selecting the Reorder Drawing Curves tool. As a reminder, when using the CCS meshing tools, be sure to select the Add Curves to the CCS Component button before creating the mesh or exporting. The Export button can be used to create a CSV file for the CCS component, which can be uploaded to FlightStream at any time. Now we will go over how to use the Unite tool. The purpose of the Unite tool is to create a watertight exterior surface mesh that is suited for flow simulation. The first thing to do is to check that the surface normals for each mesh is pointing outward. We can do this by using the Green Box Info tool in the toolbar to highlight each mesh, either green if the surface normal is pointing outwards, or red if it is pointing inwards. We can then select any mesh that has an inward surface normal and use the Reverse Surface Normal button to flip the normal outwards. After opening the Unite window from the Mesh dropdown, be sure that you have defined the location of the openvsp.exe file before selecting the Unite button. This is necessary for the Unite function to work properly. Additionally, remove any free edges from the mesh before using the Unite function. Free edges can be located by going to the Diagnostics window, hitting the Refresh button, and then selecting the Free Edges option to highlight them in the graphical window. Now that we've created our mesh, we will create a half model for use in our simulation. In the Mesh dropdown, select the Repair option and open the Repair window before navigating to the Cut tool. Select the XZ plane to cut along the center line of the fuselage and vertical stabilizer. Then, in the Mesh dropdown, choose the Select Mesh Faces by Threshold option. Here, we'll use the threshold parameter in Y for a plane at 0, and then the threshold logic will be set to below, and we'll toggle on the Delete Selected Faces option. Now that we've created our half model, we can set up our runtime parameters. Set the angle of attack to 10 degrees, toggle the freestream velocity to freestream Mach number and set that to 0.3 along with the reference Mach number. Now we'll use the ruler to define our reference length. It is approximately 5.6 meters, so we'll fill that in. Then we'll select our wing, and in the Query Selected Mesh Entities tool, we'll look at the projected area in XY. As we are using a half model, for the proper calculation of our aerodynamic coefficients, we should double our projected area to get the total wing area. Now we will define our trailing edges and wake termination nodes using the Auto Detect feature. Now we will declare our solver settings. Under Steady, the Vorticity CDI boundaries should consist of any mesh component that has a user-marked trailing edge boundary condition. Under the Flow Separation dropdown, the axial boundaries should be set to any geometry component that has an airfoil type shape. More information for each of the solver settings can be found in the user manual. Finally, we'll select Solver Initialization from the toolbar. Then, in the Model dropdown, for a Mach number of 0.3, we will select the Subsonic Prandtl-Glauert option, select the Mirror option for symmetry, and then select the Default button for the termination X location in meters for the wake. Once the solver has been initialized, the simulation can be run by selecting the Play button in the toolbar. By right-clicking in the graphical window, many customization options exist. In this case, the color map threshold for the coefficient of pressure is set to a custom range. An important aspect of CCS meshing is the ability to create, define, and deflect control surfaces. Begin by recreating the wing mesh using the CCS options as previously discussed. By selecting the Flaps and Control Surfaces button, the user has the option to create a gapped flap subsurface, a Fowler flap subsurface, or a morph flap subsurface. In this case, we will create a gapped flap subsurface. Define the name of the subsurface, the spanwise parametric location of the root and the tip of the subsurface, and then any of the other desired customization options. When preparing a mesh for simulation that has either a flap or a control surface, The user manual states that for deflection angles of greater than 10 degrees, the flap or control surface should not have wake termination nodes. For deflection angles of less than or equal to 10 degrees, define wake termination nodes on the subsurface and the wing. See the user manual for more detailed information. Note that for Flightstream 26.0 and earlier, meshes with subsurfaces must be uniformly distributed. For Flightstream 26.1 and beyond, meshes with subsurfaces will be compatible with growth rates and clustering. Thank you for tuning in to this Flightstream tutorial.